Okay, good day. This is Honors Algebra 2. I am Mr. McCully, and this is the video presentation for section 10-14 on infinite geometric series, not just the finite ones, but the infinite ones. Let's get right to it. Today we are going to find the sum, if possible, of a infinite geometric series, and then we are also going to write a fraction for the repeating decimal. So first off, let's have a couple of definitions. Excuse me. First, an infinite geometric series is a geometric series with an infinite number of terms. A divergent infinite geometric series is an infinite geometric series with no sum, and a convergent infinite geometric series is an infinite geometric series with a sum. And so your first question, hopefully, is how can I have an infinite number of terms, add them up, and it actually come up with a number? Why isn't it always infinity? Well, let's explore that here very quickly. So first off, we have two geometric series that are kind of related to each other. And if I start with this first one, 1, 3, 9, 27, 81, 243, you'll notice that the common ratio to this thing is 3. And every time that I multiply by 3, I'm going to get a bigger number. So no matter what happens, if I keep going to the right and keep multiplying by 3, these numbers are going to continue to get bigger. And what happens when they keep getting bigger, this sum is going to grow without bound, and therefore it will be divergent. Divergent. I think that's right. Divergent. Yes. Okay, we're good. But when I look at this one here, I just flipped those numbers around. I started with 243 divided by 81. Divided by 3 gives me 81. Divided by 3 gives me 27. Divided by 3 gives me 9. Divided by 3 gives me 3, and so on. And so the next numbers, though, they're going to get really small really quickly. And eventually, if I get a third, will be my next one, and then the next one will be a ninth, and then the next one after that one will be 127th. And so these numbers that I'm adding get to be so small that it eventually becomes insignificant. And the result of that is we have this equation. The sum of a convergent geometric series is this, and it's S. There is no S sub n here because we're adding up not a certain number of terms, but we're adding up an infinite number of terms, is the first term divided by 1 minus r, provided that r is less than or equal to 1. Now, you'll notice that this is similar to the equation from the last section, which was S sub n equals a sub 1 times 1 minus r to the n power over 1 minus r. Now, this one does not, or the one that we're working on, does not include this portion of the equation. And there's a reason for that. If r is less than 1, so let's just do a quick exploration here. So let's say I do 0.5, and I raise 0.5 to the second power. I get 0.25. 0.5 raised to the third power. I get 0.125. 0.5 raised to the 10th power. I get something close to 0. So if you have a number that is smaller than 1 and you raise it to a power, the result is going to be even smaller yet. So much so as n goes to infinity, r to the n is going to tend to go to 0. And again, we see that at the 10th, even at 0.5 to the 10th power, it would be 0.00030 zeros, and then we'll get a 9. And if we're talking infinity, clearly this is going to go almost to 0. So much so, 1 minus 0 is 1, and then 1 times a sub 1 gives me just a sub 1. And so this expression, as n goes to infinity with an r that's less than 1, tends to just go to 1. All right, So let's find the sum of the following geometric series if possible. If not, label the series divergent. So this first one here, I've got 16 plus 8 plus 4 plus 2 plus 1. And clearly in this one, my R is going to be a half, my common ratio. 16 times a half is 8, 8 times a half is 4, 4 times a half is 2, and so on. R is clearly less than 1, so we can set up this sum. This is a convergent series, and we can say that S is equal to a sub 1 over 1 minus R. In this particular case, it'll be 16 divided by 1 minus a half, and 1 minus a half is a half. And if I divide 16 pies into halves, the result will be 32 halves of pies. And so there is my result there. So for this next one, 1 times 3 halves is 3 halves. 3 halves times 3 halves would be 9 fourths. 9 fourths times 3 halves is 27 eighths. 27 eighths times 3 halves will be 81 sixteenths. So we have an R here of 3 over 2. Now, even though it's a fraction, 3 over 2 is bigger than 1, so this is a divergent series. All right, let's look at this one. If I look at this summation notation and I plug in I equals 1 to infinity. The first term, when I plug in I equals 1, it'll be 100 times 0.9, which will be 90. And then 0.9, or the second term, would be 100 times 0.9 squared. So let's do that. 100 times 0.9 squared. We won't go very far because we won't need to. Will be 81. And then let's just go second answer. Oops, let's go second entry here. There we go. And let's raise that to the third power. You get 72.9. And clearly these are getting smaller. But what is the common ratio? If I look at this expression here as start one more time. If I look at this expression right here as the equation for a geometric sequence, a sub n equals 100 times r, 0.9 is our r. I gave it away to the n minus 1, and it's not quite that because I have this, and my first term will be 90. But we can clearly see that this 0.9 is our common ratio, and r equaling to 0.9 is less than 1. So this thing is going to be a convergent series. So I can go S equals, this one has a first term not of 100, and it's not 100 because it's not I minus 1 up here. It ends up being 90 over 1 minus 0.9. Well, 1 minus 0.9 is 0.1, and 9 divided by 0.1 would be 90. All right. Okay, quick exploration. We all know that 0.3 repeating is 1/3, and 0.3 repeating is 0.33333 ... on for forever. Well, let's look at this in the terms of a geometric series. I could rewrite this as 0.3 plus 0.03 plus 0.003 plus 0.0003 plus 0.00003, and so on. And clearly these numbers are getting smaller, but by how much? What times 0.3 is 0.03? Well, 0.3 times 0.1 is 0.03, times 0.1 is 0.003, oops, times 0.1 again will be 0.0003. So clearly our common ratio is 0.1. So here is our first term, a sub 1, and our common ratio is 0.1. So the sum of this infinite geometric series is going to be 0.3 divided by 1 minus 0.1. All right, well, what is 0.3 divided by 0.9? Okay, if I were to do it just regular without a calculator and do it in my head, we would move the decimal places. We get 3 over 9, and that's okay because we multiply by 10 over 10. And then 3 and 9 have a common factor of 3. If I divide 3 by 3, I get 1. If I divide 9 by 3, I get 3. So there is our 1/3. Now we can do that with any repeating decimal. So if I look at this one, what is 0.4148 repeating written as a fraction? It'll be 0.148, 148, 148, 148, and so on. I can break that up into an infinite geometric series by going 0.148 plus 0.123. So I need 3 zeros to take up those things, and then 148, and then plus 0.123. That takes up the first 3 terms, and then 123, that takes up these 3 terms, 148. I think you get the picture. And so if I want to move it 3 decimal places instead of just 1, what do I got to multiply? Okay, well, let's take a gander. If I got 0.148 and I multiply that by 0.00, I think that might be too many places, 0.001 there. I'll come back here. 1.48 times 10 to the negative fourth is what that says. That I have a decimal place. I have 1, 2, 3, and then the fourth term there will be the 148. So I'm getting what I need to have there. All right, so this clearly tells me that my common ratio R is going to be 0.001. So my sum is going to be that first term, 0.148 divided by 1 minus 0.001. All right, now I'm not going to try and do that in my head. So let's grab our graphing calculator and go 0.148 divided by parentheses, because I didn't do the fraction bit, 1 minus, only 1 minus, 0.001. And just in case this doesn't come out to be a nice number, let's hit the math button, hit the fraction, and go enter, and I get 4 over 27. All right, well, that's all I got for today, folks. So the McCulley fun fact of the day: as of this recording, Mr. McCulley has never broken a bone. And since I've now put that out into the world, I am sure that karma will hit me real good and I'll break a bone shortly. But that's all I got for today, folks. Have a good day. Bye.